Okay, so continuing to play around with properties of determinants, we're going to take the determinant or find the determinant of this matrix. Notice this matrix has some variables in it, x, or a variable, x I should say, and so our determinant is just going to be a function of that variable, function of x. And so this is pretty easy, I hope. The determinant of a 2 by 2 we know how to find, right? It's AD minus BC. And so what do I have here? Well, let's clean this up a little bit. Here it is, but let's clean it up. If I FOIL this out, I get what, x squared. I get plus 5x minus 3x minus 15 minus a negative 7 is plus 7. And combining like terms, I've got x squared plus 2x minus 15 plus 7 is minus 8. And there is the determinant as a function of x. And now for different values of x, you can plug in and find the corresponding determinant for this matrix. Okay, that's pretty easy. Well, now what I want to ask about is for what values of x is this matrix invertible? For what values of x is this matrix invertible? So this matrix will be invertible if what? It'll be invertible if the determinant of A is, what did we just learn? It's going to be invertible if the determinant of A is not 0. So I need to find all the values of x that make this expression here, this determinant up here, not 0. So what I'm going to actually look at then to start with is, when is it 0, right? Because that's an easier question. So let's note that the determinant of A equals 0 when x squared plus 2x minus 8 equals 0. And hopefully everyone knows how to solve quadratic equations. This one's pretty easy. It's already set equal to 0. If I can factor, I factor, and in fact I can. This factors is what? X plus 4 times x minus 2. And therefore x is what? Either negative 4 or positive 2. All right, but that's when the determinant is 0. So what am I going to answer then here? What values of x is the matrix invertible? So A is invertible for all values of x not equal to negative 4 and 2. Okay. Or if you want to use set notation, you can say the set of all x, vertical bar meaning such that x is not equal to negative 4 or 2. Okay, so be careful, as invertible means anything except negative 4 and 2. If I said when is it singular, the answer would just be x is negative 4 and 2, right? Because when it's singular, the determinant then is going to be 0. Talking about being singular, let's look at this example. For what values of x and y is this matrix singular? Okay, so now singular means what? That the determinant of t is 0. All right, so let's find the determinant of t. Well, this is a 3 by 3 matrix, so I'm going to do cofactor expansion. And how am I going to do cofactor expansion? Along what row or column? Well, there's only one 0, so I'm either going to use the first row or the second column. I'll go cofactor expansion along row number 1. So first entry is x times it's plus 1, right? As far as the cofactor goes, right? Remember, it's plus minus plus minus plus minus. And then it's minor. All right, take out that row and column. Plus what? Well, 0, and then plus 1 times its negative 1 to what? 1 plus 3 is negative 1 to the 4th is positive again, right? Positive, negative, positive. So I'll just put positive 1 there. Times its minor. Take out that row and column. We've got 2, 1, 4, 2. And let's compute these determinants. So this one is going to be negative 6 minus 2y. 1 times negative 6, 2 times y. Plus 0. And then this is going to be 1. And what's this? 2 times 2 is 4. 1 times 4 is 4, right? So that's also 0. And we found our determinant. The determinant of t, I'll write it this way, is, I'm going to factor out a negative 2 out of here, negative 2x, and that leaves me positive 3 plus y. Okay. So the question is then, what we're asking for what values of x and y is the determinant of t equal to 0? Okay. So t is going to be singular when this determinant is 0, and that's going to be for what values? Well, when x is 0, certainly it's going to be a determinant of 0. What would y have to be? If x is 0, y could be what? Anything. If x is 0, y could be 20. 0 times 23 is still 0, right? And so t is singular when x is 0, and when y is any parameter, we'll say t. Or, what else can happen? Y could be negative 3, and then x can be anything. So x is r, y is negative 3. Obviously, if x is 0 and y is negative 3 is one possibility, but be careful, it's not the only possibility. There's actually infinitely many combinations. So if x is 0, or if y is negative 3. Not both. They don't have to both be. Certainly if they both are, then that's true. But we really got an or situation there. Okay, so singular, again, we're looking for when the determinant is equal to 0. Non-singular when the determinant is not equal to 0. Okay. I want to close then with a formula for finding the inverse of any matrix. So you remember how we found inverses before? We did the inversion algorithm, right, where you took the matrix and joined the identity matrix and then did row reduction until you got the identity matrix on this side and the inverse on the other. Well, here is a nice formula for you. If you're an engineering student, you like formulas maybe. A, first of all, is a square matrix. And we're going to first of all create what is known as the matrix of cofactors. All right, so what I'm going to do is I'm going to compute the cofactor for every entry. So remember what the cofactor is. It's negative 1 to the I plus j times the minor of that entry. And I'm going to replace each entry with its corresponding cofactor, which would be a real number, right? And so I'm going to get a new matrix that's called the matrix of cofactors. And then I'm going to take the transpose of this matrix. That transpose is what we call the adjoint, and it's denoted ADJ. So once we have the adjoint, then the formula for finding an inverse of any invertible square matrix is this. The A inverse is 1 over the determinant of A times the adjoint of A. You say, wow, that's a great formula. It's very nice. Let me show first of all that it works for a 2 by 2 matrix. So if A is A, B, C, D, I'll just do, instead of A11, A12, and so on, I'll just do A, B, C, D. First of all, I need the determinant. We know that is easy. AD minus BC, we already know that. And then I want to compute the matrix of cofactors of A. Matrix of cofactors of A. So how do I do that? I just find the cofactor for each entry. So what's the cofactor of A? Well, it's negative 1 to the first row, first column, 1 plus 1. So negative 1 squared is positive 1. And look at its minor. It's just the 1 by 1 matrix D. So that's going to be a D there. Okay. What's the cofactor for B? Well, now it's -1, first row, second column. -1 to the 1 plus 2. -1 cubed is -1, and its minor is C. So -1 times C. C is what? Second row, first column, -1 to the third power is -1. Its minor is B. So that's -B. And then D, -1 to the 2 plus 2, second row, second column, is -1 to the fourth. It's +1. Its minor is A. +1 times A is A. So there's the matrix of cofactors. The adjoint is the transpose. So the adjoint of A will be the transpose of this matrix. Right? So this row becomes our first column, and the second row becomes our second column. And that's the adjoint. And by the formula, it's 1 over the determinant of A times the adjoint of A. So for a 2 by 2 matrix, I get 1 over the determinant of A times the adjoint. And I hope that this looks familiar. This is the formula we gave you way back when we first introduced the inverse for a 2 by 2 matrix. We proved it worked then, but didn't really say where it came from. And the answer is now it comes from this more general formula. So for a square matrix 2 by 2, then we have this form of the formula. 2 by 2 is not bad because computing cofactors is easy. 3 by 3 wouldn't be bad either for this formula. Okay, but remember, computing cofactors, pretty costly, right? So if you have an n by n matrix, then you basically have n minus 1 factorial computations for each cofactor in general. And how many cofactors are there, by the way, to compute? There's n rows and n columns. N times n is n squared. So it's n squared times n factorial, which is n squared times n minus 1 factorial in terms of computations. So that's n times n factorial. And if you think about that, this formula is not very efficient. It gets very costly, and so computing an inverse using this formula is not the way to go. But on the other hand, it is a nice compact way of writing the inverse, and it could be helpful in proving certain things, which we actually will use this to prove something called Cramer's rule later on. Okay, so this ends our discussion on determinants. You can see from this last couple of videos here, though, important properties relating the determinant of a matrix to whether or not the matrix is invertible, and then having this nice formula for the inverse of a invertible matrix.